Through 10 games of basketball this season, you have made 22 out of 24 of your free throws. Which word or phrase describes the probability that you will make your next free throw? Remember, this is what probability is about. Usually, it is used to make decisions in the future based on something that has occurred already. And so for this one, we see that if we were to show this as a fraction, you've made a total of 24 free throws, and of those, 22 have gone in. So you've made them, I guess. That's pretty high probability. If I were to use my calculator on this one, 22 divided by 24, I get a pretty ugly decimal here, 0.916 repeating, which really comes out to, it's about 91.7%, which is pretty high. It's definitely higher than 50%. That would mean it's likely. Remember, impossible 0%, unlikely is less than 50%, equals 50%, likely is more than 50%, and then certain would be exactly 100. It's close to 100, it's just not quite there. Here's the objective for the day. I can use the fundamental counting principle to determine total number of outcomes or results. Remember that last time we saw that the total number of outcomes or results was the denominator in the fraction when we set up probabilities as fractions. And yeah, we can see that right here. Total possibilities of results. For these ones, I don't think we're necessarily looking for the overall probabilities. We're just looking at possible results or possibilities and results, which again would be, it helps us, the fundamental counting principle here helps us to figure out these denominators. So the fundamental counting principle, if two or more situations happen, multiply the total possibilities by each other. They can be the same situation happening more than once, such as rolling a dice and then rolling a dice. Of course, rolling a dice has 6 possible outcomes, and then rolling another dice has 6 possible outcomes. What we're saying here is that we're going to multiply these totals together, which indicates that this would be 6 times 6, and so there's 36 possible results. Now, when we start breaking these up, we may see that some of them look kind of similar. But really all we're concerned about is knowing that there's going to be 36 possible results. We'll also look at a different way to figure these out, but it's possible you could roll a dice, which would have 6 possible outcomes, and then spinning a spinner, depending on how many there are. Let's say that there's 4. If you were to multiply these two together, and again, these 4 we're saying they're different, same with the dice, but that would give you 24 total outcomes from doing these two situations, these two things. Now, generally speaking, we'll use tree diagrams like this. Now, whatever these situations are, this one is only showing 2 possible things that happened first. Maybe that was tossing a coin. Maybe you got heads and tails. Maybe you're choosing from 2 colors, blue or red, something like that. And then you can choose from 3 different options there. Now, notice it's the same 3 for both A and B from the first situation. That's because you're doing the same thing. Maybe this is, I don't know, spinning a spinner with 3 sections in it. So you could spin 1, 2, or 3. But it doesn't matter what happened the first time. Even the second time, no matter what happened there, you'll get a 1, 2, or 3, or a 1, 2, and 3, okay? And then the third situation, again, maybe it's only got 2 options there. Heads or tails, maybe some kind of color, something like that. But again, you notice that it repeats because it has the same options no matter what has occurred before it. Now, what you see here at the end there, this arrow's pointing to the actual outcomes. So this tree, this part of the tree right here going through these branches would produce the results A, 1, and then S. Or maybe this one, if we went from A to 1 to T, it would be A1T. And so it kind of creates what some people even consider a mapping. A tree diagram also works. Sometimes people do it vertically. I have mine set up horizontally. But again, the idea here is, well, how many results are there? And we could count these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 outcomes. Well, how did we get 12? Well, if we use the fundamental counting principle, which is what I would encourage you to do, the first situation had 2 possible outcomes. The second situation had 3 possible outcomes. And then the third situation had 2 possible outcomes. You could have just multiplied these together and then gotten 12 possible outcomes, okay? So right here we counted 12 outcomes. But by using the fundamental counting principle, we kind of took a quick shortcut, and we also found there were going to be 12 outcomes. Now, the tree diagram is nice because it does list all of the outcomes. But again, if all you wanted to know was how many outcomes there are going to be, you could have used the fundamental counting principle. Let's look at this one. You're organizing textbooks on your bookshelf. You have a math textbook, a biology textbook, and a history textbook, and also a writing textbook. That's 4 books. I'll have to make a mental note of that. And then how many different ways can you line the textbooks up in your bookshelf? So there are 4 books. That'll be important to know. And we're going to line them up, so that means we got 4 positions. Now, the thing we need to remember on this one is as we place one book on the shelf, it takes one away from our options. Okay, so in other words, let's look at the shelves here. So I'm going to list these out. Or I guess the order of the books, and we'll say these are positions, okay? So starting as far to the left as I can go, I'd have the first position. Then I would have the second position. Then the third position. And then the last book, since we've already placed all the other 3 books, last position, 4th position here, is automatically going to just be one final book that remains. Okay, so if I wanted to create a tree diagram from this, so I'll just go in order here. We got, what do we got? Textbook. We got a math textbook, which I will show with just the letter M. Biology will be B. History will be H. And then writing will be a W, okay? But again, I'm going to just start with my math textbook. So if the first position takes the math textbook, then I have 3 options that are left for my second position. Okay, and those options are given up there. We got biology, we got history, and we have writing. So B for biology, H for history, and W for writing. And from there, I can split these up even further. So biology now, but now since I've got 2 books on the shelf, I've only got 2 left over. I can either take history or writing. If I was at history, then I could take maybe biology or the writing one. If the writing one goes on, then you can either have the options of biology or history. Either way, we come to the end here. So on this one right here, I have math, biology, and history, which leaves me with just the option of writing in the 4th position. If I put writing in the 3rd position, then it's possible that history could be there. And then I just go down the line. And again, sometimes this is just kind of common sense when creating the tree. So there in the 3rd position with biology, maybe the writing would be there. If the writing was 3rd, then biology would be 4th. And again, biology being 3rd would make history the 4th position. If history is the 3rd position, biology would have had to be the 4th position. Okay, so I can list my outcomes in order of position, right? So I could say here, the first one, this one, I had math, then biology, then history, and then writing textbooks. And I can do this all the way down the line. So again, the first book was still math, and it was math for all of the outcomes, right? So I'll just put the M there. And then the next one was biology, then writing, and then history. On the next one, again, you can follow through on the branches. Math to history to biology to writing. So math to history to biology to writing. Or math to history to writing to biology for this next one. Or the next one, math to writing to biology to history, or math to writing to history to biology. And so I could have these books in this order right here, but that was just with math being the first one. And the truth is that I would have to do this for not just math, but then biology and then history, and then writing as well. Okay, but again, I'm not going to go through and list all these. In fact, I think I will list them all, but I'm not going to go through them. So here they are. So there you go. Well, that's a lot of options. Now, I think somebody could have deduced this from before, but we saw the M, with the first position, had 1, 2, 3, 4, 5, 6 options, which means each of them will have 6 options, right? So it would have been 6, 12, 18, 24. And so pretty much right off the bat, I think some of you guys could have told from the beginning there would have been 24 results or outcomes. Okay, so, and that answers the question. How many different ways can you line the textbooks up on your bookshelf? 24 ways. Now, besides that, again, the nice thing about the tree diagram is it gives us all of the different combinations that could occur. If you have math first, biology first, history first, or writing first, we can see all the different combinations. All 24 of them in order. But again, we could have used the fundamental counting principle if we wanted to. For example, in the first option, you would have had 4 books to choose from. In the second position, you would have had 3 books to choose from. And again, that's because we had used one of the books up, and then using another book means we would have only had 2 options in the second position, and then finally just 1 position on the third one. As it turns out, if you take 4 times 3 times 2 and then multiply it by 1, you do get the 24 results. And so again, the fundamental counting principle, it didn't ask for the outcomes on this one. I was just showing it so that you know how to use a tree diagram if called upon to do so. But the truth is, in the future, for the rest of the problems, this is all I'm going to be doing right here. Now, of course, it does take some time to get used to the fundamental counting principle. But as soon as you can get it, you can arrive at how many outcomes there will be pretty quick. So on this one, how many different possible outcomes are there if you spin a spinner labeled red, blue, yellow, green, purple 3 times? Now this one's a little bit different than the last problem. Okay, now not just because there's not 4 positions, but and then there's spinners. So you got the first spin, right? Then you're gonna have the second spin, and you're gonna have your third spin. There we go. Okay, so for these spins, you have options, right? Now again, we're saying that there's an equal likelihood of spinning these colors, but what colors do we got? We got red, we got blue, yellow, green, and purple. So I counted that. It's 5 colors. Okay, so the first spin, you would have 5 colors to choose from. Now, this is where it becomes different than the last problem. It's not like we've used up one of the colors and it's no longer available, so that there's only 4 colors on the second spin. No, there's still 5 colors in the second spin, and even 5 colors in the third spin. Now, again, you could figure these out, how many there are, but you're going to see pretty quick that this number is going to get pretty high. If you multiply these together using the fundamental counting principle, which is what I would do, this gives us 125 outcomes. Now, as fun as that seems to list all these, I'm not going to. All I want to know is this is how many possible outcomes there are, and that is the fundamental counting principle. So you kind of have to think about each of the situations that you're looking at and use the information that's given to figure out how you're going to use the fundamental counting principle. I'd like to list the things that we're having. So, for example, you are trying to pick out an outfit for the first day of school. You can choose from 2 pairs of pants, 2 t-shirts, and 4 pairs of shoes. How many different outfits do you have to choose from? So we have 3 different articles of clothing that we're looking for here. We got pants, we have shirts, and we have shoes. Okay, but from this information, once again, by using the fundamental counting principle, we should also be able to figure out how many outcomes there are. So let's start with pants. How many pants do we got? We got 2 pairs of pants. You see, you got 2 options there in the first, I guess for us, the first article of clothing. You got 2 t-shirts, so there's only 2 of those. And you have 4 pairs of shoes. All we're going to do is multiply these together. 2 times 2 times 4, this one actually has less, gives us 16 possible outcomes. So that's how you use the fundamental counting principle. But again, we had to figure out, what articles of clothing did we have to choose from? Pants, shirts, shoes. If you wanted to add socks in there, you could, and make that part of the outfit, or perhaps other articles of clothing, necklaces, jewelry, something like that. But this is all we got to do in order to figure out how many outcomes there are. So if they were asking for a specific outfit, this helps us to figure out at least the denominator in the fractions that are given, or the fractions we're trying to use to find these probabilities. So this next one, you're designing a new board game and are trying to figure out all the possible outcomes. How many different possible outcomes are there if you roll a fair dice in the shape of a pyramid that has 4 sides labeled? So this one's not a regular 6-sided dice. For us, this is it's a pyramid, so it only has 4 sides. That's kind of the key word there. I really don't care about it having the options 1 through 4 if I'm using the fundamental counting principle. If I was trying to list all of the outcomes, then I would probably care what those numbers were. So we're going to roll the dice. Then we're going to spin a spinner, and it has 5 equal sides on it. Okay, so the spinner, I don't really care that it's a spinner. I just need to know it has 5 equal sections on it. And again, I don't really care about the labels. Monday, Tuesday, Wednesday, Thursday, Friday. 5 days, I guess. And then we're going to spin another spinner with 4 equal sized sections. And again, that's the crucial piece of information there is 4 equal sized sections. I don't really care that they are colors or what colors they are. So I'm going to list these. Okay, so we're going to roll the dice. Then we got the first spinner. So I'll even call it the day spinner because it's based on days. And then we got the color spinner. So the fundamental counting principle, once we get these, it will tell us the total number of outcomes. Okay, so the dice, it has 4 sides on it, right? So there's 4 possible options with the dice, just to start with. Then we will spin a spinner, but it has 5 days on it. And then the final spinner with the colors on it has 4 colors on there. So again, the fundamental counting principle tells us we can just multiply these out. 4 times 5 is 20 times 4. And again, I wouldn't want to label all or find all 80 of these outcomes, but you could. And you can imagine how big that tree diagram would be and how long that could possibly take. But we don't really care about that. If you want to use the tree diagram, that's fine. I'm not going to. I like the fundamental counting principle because all I want here is the number of outcomes. That's it. Right? Figure out all the possible outcomes. We did it. So there's our objective. Hopefully you feel comfortable using the fundamental accounting principle to determine total number of outcomes and results. Of course, since we're getting used to this kind of stuff, I don't really care what the results are. All I care about is that you can figure out how many there are so that you can start figuring out your probabilities. That'll do it for this lesson.